Science is thanks to Simone Borghesi, one of the co-author of this paper from EUI, means for European University Institute, and a colleague of my department, Ilaria Colivicchi, Department of Economics Management of University of Florence. As you can see from the title, the paper deals with insurance choices. So, as we'll see, present a model of what is called a co-insurance weight. So firms have to choose this partial coverage. And there is also a relation with an interaction with an emission taxation. And very, very thanks a lot to give me this opportunity to your at Gerald. Okay, it works. Why a paper on insurance? Insurance is considered an instrument to adapt economic agent for climate change, or if you prefer, changes in climate. Indeed, the literature emphasizes the role of this instrument, in particular with respect to the cat bond, the other financial instrument used, since it is a private, also market-based instrument to favor this adaptation. For changes climate or climate change adaptation, I mean a damage. I mean a financial damage that we'll see in risk theory, we call it a loss, only it. It's only an environmental economics approach, not an environmental science approach. Okay? So the idea is that pollution generates natural extreme events that generate a loss, financial loss. In the last, you can see the paper is very, that I cite are very, in the last years. For example, the last one in 2017 is probably one of the first in which the authors investigate the possibility of an interaction between insurance policy, that is said a private instrument, with environmental policy, so a public one. What's the empirical evidence? This is a theoretical model. We try to explain the real world and come back the results from the model to the real world examples or evidence, empirical evidence. The emphasis of I cite only 4 papers because in the slide can be the space for several papers, but it's a huge literature on insurance, environmental insurance, especially for flood insurance, thanks to the data from the National Flood Insurance Program from the United States, in particular for the price of for the house, the coverage of the house owner, the effect of the deaths, and so on. If the price of the house internalize a risk, etc. However, this empirical evidence, emphasize the role of insurance in case of natural disasters, so especially flood and coastal flood. What is strange is the low insurance coverage chosen by the house owner, the agent, because a low insurance coverage means that is a low risk that is transferred from insured to insurer, so to the insurance company. The last 2 items are very related to the results of this paper. There is a lot of evidence that the demand for insurance in general, but in particular for environmental insurance, is inelastic. And if a firm, an agent, has a high environmental risk exposition, then this elasticity decreases. So, then this elasticity is more inelastic. This means it's less elastic. I prefer to use less or more elastic than less or more inelastic because it's probably more more standard in textbook of microeconomics. So higher exposition to the risk, it means that a less elastic demand for insurance. What theory said? Well, in particular in the 80s, but also in the 90s, there was an interesting literature to understand why a firm asks for insurance. Reasons are mainly two. The first is the transfer of risk, so this risk shifting. The second is cost savings. We are in a capitalism system, so with insurance, there is a tax advantages or a cost reduction. Consider that this paper of Macmillan is one of the most important papers on corporate demand for insurance. And in general, this paper more or less published in this journal, in the Journal of Risk Insurance. Only in the last year, particularly with the SEOG, start to analyze, to investigate a strategic reasons such that firms ask for insurance. The paper of SEOG, 2006, using a Cournot competition framework, is the first in which the insurance coverage first is chosen, because in the other model, insurance is mandatory. Also in the empirical, there is also empirical papers in which they show that coverage that a chosen not mandatory coverage is more efficient than mandatory coverage. And so the SEOG is the first in which the insurance coverage is a function of the output choices. Usually it's said, or the coverage is mandatory, or the coverage is full, then it isn't, the demand for insurance isn't a function of the output choices. And very last year, in the best journal of dynamic games, we introduce endogenous random loss, but in evolutionary setting. So if SEOG, there is a symmetric duopoly in which the loss is, we have two types of, he analyzed two types of loss. A random exogenous and an endogenous, but deterministic. The first, that is exogenous, in the firms knows only the mean and variance. So indeed, the paper is in the mean variance preferences. And the endogenous loss is a deterministic one. So the author assumed that the loss is a function, is a deterministic function of the output. In the paper with Hilaire in Dynamic Games and Application, he introduced the endogenous random loss, as we see with only two states of the nature for due to complex computation. And in the paper, in analyzing evolutionary settings, so there's a population of firms, which a firm can have three types of strategy. And we have a strategy was to be green, less polluting, or brown, less polluting and risk averse, or pure green and risk neutral. So the paper, the advance in the paper is more on evolutionary setting, more on evolutionary game theory than in the theory of insurance demand. What's new? First, asymmetric duopoly. As we see, we have a clean and dirty, very, very easy. Clean, not pollute, dirty, pollute. We introduce emission taxation, while in all the other papers, there isn't an environmental policy. We analyze the role of insurance market. In the previous paper, due to the complexity, also using computations, also using simulations, it's not easy to understand the role of insurance market. Here is clear. And also is clear thanks to strong analytical results that are perfectly in line with the cited empirical literature, and also we come back to the model. So would like to highlight that this paper is more in line with the theory of insurance demand than from a methodological point of view. We can start to introduce the model. Okay, first, we assume that we start with the output market, because I said that we have the output market, and then obviously we have to introduce the insurance market. The output market, we have seen that firms are only two types: clean and dirty, very easy. Clean without pollution, only dirty firm produce. We assume that the duopoly is vertically differentiated. So as you can see here in the inverse demand function, PC stands for the price of clean good, PC the price of dirty good, C and D, so for all the rest of the paper, stand for clean and dirty respectively. We have that the intercept of this linear demand, so the willingness to pay of the clean consumers is high. This means that follow usually environmental, economic literature, both empirical and theoretical, that consumer reward firms that produce using renewable energy or using, for example, solar system again, or they take care to environmental product. Also, there is also the case on greenwashing that George knows well. However, in general, consumers are more willing to pay for a clean product, a green product in general. And with the capital Q, we denote the total output. So we'll see total output of capital Q, C total output of clean firms, and capital QD total output of dirty firms. Loss distribution. The pollution generated by dirty firms causes natural extreme events, so a loss. This loss occurs with a given probability eta. So we haven't mitigation. I emphasize that mitigation means that economic agents or environmental or the government can reduce the probability that an event occurs. This is mitigation. We don't deal with mitigation, but we deal with adaptation. So the eta is fixed. There is this loss. For the sake of simplicity, the loss is the same for both firms. Why? Think, for example, to local industrial system. I don't know in the North America, but in Europe, there is also the tradition that firms that work in the same market are located in the same geographical area. For example, in Florence, there is an industrial on silk, for example, or in textile in general. Not far, we have chemical firms and so on. And for example, also in the flood that occurred in the Florentine area, not in the Florence city, but very near, 50 kilometers far from here. In November, there is a flood, and the most important damage of this flood are in the storehouse, so in the firm deposit, more than the house. So it's like to see why corporate demand for environmental insurance could be interesting. I add to this a real world motivation. From the next year, the Italian law said that each firm has to be insured from natural events. So for the first time, we have that the government impose an insurance coverage. It is an insurance coverage different from, very different from an insurance company from the view, for example, for the cars, for the transportation insurance. Because in that case, there is the cost, the risk is transferred to all the insured. In this case, the risk with a natural extreme event, the risk is from insured to insured. So it's quite different. I don't know when it will be the application of this law, because usually the law like this is applied after some years, but it's a very important change, also, at least in the law, but also in the economic behavior of the corporate, of the firms in general. And the last distribution has only two states of nature, for the sake of simplicity, obviously, but it's quite used in this literature to start from the seminal work of Smith, Journal of Political Economy. And we assume that this X, for example, X, I don't define it, X is the state of nature in which the loss occurs. And as we'll see, is a function of the dirty output. So probability eta, the loss occurs, probability 1 minus eta, the loss does not occur. We can go now to insurance market. We assume that both firms are risk averse, so they can protect themselves from the loss, stipulating an insurance contract. For simplicity, we don't assume a deductible. We can arrive to the same result with a more difficult, in particular for computation, difficult, using the deductible deductible contract, but using a coinsurance contract or an insurance coverage. So the firm have to choose a coinsurance rate beta between 0 and 1. When beta is equal to 0, means that the firm is not insured, equal to 1 full insurance, between 0 and 1 partial insurance. And insurance premium is given by the expected value principle. So capital pi, the insurance price, is equal to mu, that is the expected value of the random loss, times beta, the insurance rate, insurance coverage. So this is the expected indemnity. Mu times beta is the expected indemnity, times 1 plus lambda. What is lambda? Lambda is the loading factor. This is a parameter that captures all the cost that the insurance company support to stipulate this contract. We assume that insurance markets are competitive. So beta chosen is the beta that this agent, in this case this firm, find in the market. As Mossin proved in 1968, if the premium is fair, so if lambda is equal to 0, then the optimal choice by the firm is a full coverage, as also we see in the paper. Now, we can go to profit function. The random profit is composed of operative profit minus the premium minus the loss, XTID, plus the indemnity. So if beta is the coinsurance rate, 1 minus beta is the retention rate. Okay. The loss, as standard in the literature, the loss is restricted over the interval 0 operative profit, so wealth, the wealth of this firm. The games is a sequential games, so it's developed in 3 stages. I don't define for the moment the operative profits, that as we'll see is output revenues minus cost, because it's not important. It's important in the stage in which the firms has to select the output. So the dynamics of the game is, in the first stage, firms choose the strategies to adopt. In the second, the output. In the third, the insurance coverage. So obviously the game is solved in backward induction. So the main research questions are, which type of firms ask for more insurance? So clean or dirty? Well, behind these questions, the real question is, who the insurance help? The insurance help clean firms or dirty firms? If obviously insurance help clean firms, insurance is sort of it's a good news. Okay, can help the clean firms to remain in the market, at least to have a more a higher profit. But if insurance help dirty, then be seen as not the devil, but it's not a good news as if it helped the clean firm. First question. Second, what is the effect of taxation on the demand for environmental insurance? So if we increase taxation, what happened to the insurance coverage? Similar questions are in the empirical evidence to the subside. So subside is usually we can see it as the opposite sign of taxation. And the third, the most important, can the insurance market have a role in the green transition? So again, if we increase the loading factor, so the insurance premium, what happened to the strategy selection? This affect the selection strategy by the firm. We will answer to these questions at the end, obviously at the end of the presentation after introducing the analysis of the model. So we can start with stage 3, insurance choice. Well, we adopt a logarithmic utility function. First, big assumption, probably the most important assumption in this model. Why? First of all, because a log function is a constant relative risk aversion function, utility function, with a constant relative risk aversion coefficient equal to 1. And the CRRA utility function is the widely used utility function. Why? Because it has this constant relative risk aversion that in economic theory is considered as an important property, with respect to other utility function that we talk about a little bit after. And second reason, using the log and not isoelastic utility function is easier from a computational point of view, as you can see in this proposition. And the third, and it's important to see a constant relative risk aversion utility function as a decreasing absolute risk aversion property. And this assumption, particularly the Dara property, more than a constant. The constant, both, but in particular, so as we will see in the questions, in part of these questions, the answer is given by the assumption of a Dara, or by the assumption of a constant relative risk aversion utility functions. We'll see, talk about better with the result. Firms have the same risk aversion, logarithm utility function. So they maximize the utility, the expected utility, and the argument of the utility is the random profit. Choice variable, the beta between 0 and 1. So since we have only 2 states of nature, we have that utility is eta times the natural log of the random profit in case of if the loss occurs, 1 minus eta times natural log if the loss does not occur. The optimal insurance coverage is equal to 1 if the lambda is equal to 0, Mossel theorem, is equal to 0 if the lambda is greater than a threshold value, or alcohol if an agent in general is risk averse, if the insurance prices is so high, it's rational not to be insured, is between 0 and 1 if we can see this value. What is the Dara property? Decreasing absolute risk aversion. It's case that if the wealth increase, in this case, are the operating profits increasing, then the insurance coverage decreases. So this is the ratio. Why the Dara is important? Higher operating profit, as we'll see higher output means lower insurance coverage. Obviously, if both firms are clean, then the risk disappears, and clean firms demand a nil as a nil demand for insurance. The optimal insurance coverage is equal to zero. Stage 2, output. Now we can introduce operating profits. The difference in the production can be only in the fixed cost. Think, for example, solar production system, renewable production system. The problem is not a renewable production doesn't mean higher marginal cost, but means a very important fixed cost. This is a parameter phi. Differently, the dirty firms has the same production revenues, so P minus theta are the revenues, so minus cost. Theta is the marginal production cost. The dirty firms has to pay an emission tax. Very, very easy. A unit fee on one output, one-to-one emission tax. For the sake of simplicity, but it has no effect on the results on the paper, we assume that the loss is a linear function of the total dirty output. So X is equal to this delta, an impact parameter strictly positive, times QD, capital Q. So the maximization problem of the REMD of the firm, sorry, is to find the Q such that the profit a maximum that is given by the operative profit minus 1 plus lambda times the optimal insurance coverage times this is the mean eta delta and QD is the mean of the loss. The optimal values are in the slide. Note that first, clean output is always greater than 0 because we denote with gamma C and gamma D respectively the clean and dirty market size. And the clean market size is always greater than the dirty market size. Second, so we have to restrict, obviously, the dirty production to the existence from the lambda that it cannot be greater than a threshold that, again, in the paper we have we describe the set of the restriction of lambda for the coexistence of beta between 0 and 1 and a positive output. Look that if the tax increases, then the output of clean firms increases. If the tax decreases, then the output of dirty firm decreases. What is the CC in D? Since it is a duopoly, the market is only a composition between clean and dirty, clean, clean, dirty. So CC, it is the output of the clean firms if both firms are clean. CD is the output of the clean firms if there is a mixed duopoly. DC, dirty output, mixed duopoly. DD, dirty output if both firms are dirty. Okay. Now we can go to the first stage. We can rewrite the optimal random profit as you can see that the Q, the output squared, so this is the operating profits, not less, minus the fixed cost in the case of clean firms, and minus this is the insurance market and the insurance market and the MAGE and the loss. If there is a positive, if there is at least one dirty firm. Okay. I remember that since the profit are the argument of the log, then the profit are always strictly positive. We can go to the interval of the existence of the strategy. Probably it's better if I show you graphically. This is a very complicated panel performed with several simulations using a toolbox very complicated MATLAB, where we have that if phi is between 0 and underlying phi, then both firms are clean, so the clean strategy is dominant. If or if you prefer, the dirty strategy is strictly dominated, to be more formal. If phi is between phi underline and phi overline, there is a mixed strategy. So exists a mixed strategy. So the firm, the market is composed of both type of firms, so mixed. And if phi is greater than phi overline, then the clean strategy is dominated by the dirty film. The dirty film is dominant. The dirty film strategy is dominant. We find that all underlying phi is always greater than 0. And the overline phi is the minimum of this QCC from here. And what are here? Here are the threshold from internal and external stability. There are two ways to solve this kind of problem, model. Or using the mixed strategy, Nash equilibrium, but there is the problem of stability of the equilibrium that in the mixed strategy approach exists only if there is an evolution. Or we can adopt, we can use the D'Aspremont, Jaskold, I don't remember the Don Simoni, I don't remember the other author, sorry, approach, so the coalition approach to adopt the case, so using internal and external stability. So, and are, as you can see, are these threshold that come from if the profit satisfied the internal external stability. Now, we can go to results in order to discuss better. First questions, who ask for more insurance? Well, we find that the dirty firm ask for more insurance than clean firm. Why? Because from the stage 2, we can see that the clean firm, so the output of clean firm is always greater than output of dirty firm. Due to the Dara property, you can see here, comparing the insurance coverage, the optimal insurance coverage, we can find this ranking. And so the clean firm demand for less insurance. So we are saying that insurance helps dirty firm. Not a good news. Not good news, sorry. Sorry also for my accent. Because as we'll see after, insurance, for example, if a reduction, reducing, I want to anticipate. Well, for the moment, we can see that this means that insurance helps more the dirty firm than clean firm. What is the effect of taxation? This is the second question on the demand for insurance. Well, an increase in the emission tax decreases the insurance, the insurance coverage of clean firm, while increases the insurance coverage of dirty firm. Why? Again, for the Dara property. Because, as said before, if tax increases, then output of clean increases too. And so the insurance coverage decreases. Differently, if tax increases here in the for the dirty firms, so for the output of dirty firms, we have that output decreases, and so insurance coverage increases. So we are saying that if taxation increases, then again, we have that insurance helps again more dirty firm. Why? Because a higher tax means lower profit so reduction the output for the dirty firm, and so they need more insurance to protect themselves from the loss because they are less richer. So they have less money, less profit to cover the loss. This is the idea. This is the intuition behind the data property. Arrow, for example, in the famous, in the most famous book on the three essay on risk theory, he said that he find economic intuition behind the data. The idea is that if a richer people, a rich agent, he spend less to cover, so as a less insurance premium, risk premium, because he spend less to cover the risk, because he can use other, sorry for the expression, because there's money to face to this risk. This is the intuition behind it. So for that reason, the data is used, and also Bernoulli in his first, probably in the first paper on the expected utility theory, Bernoulli used the square root utility function. Again, a utility function with a data. It was in the middle of 18th century, so it know that it is a data property, but again, it is, and he said it at increasing of the risk, so increasing of the lottery, so increasing of the wealth of the agent, you have a decrease of the risk in general, the exposition to the risk of the risk aversion. Okay. Now we asked ourselves, what happened if we differentiate the threshold, underlying fee and overlying fee, with respect to the two key parameters of the model, tax and the loading factor? What happened? Well, if fee underlying, for example, shift to the right, so for the partial derivative of the underlying fee with respect to tau or lambda is greater than 0, then the interval in which the screen strategy is dominant increases. So this means that it favors tau, lambda, increasing tau and lambda, favors the screen strategy. Similarly, if underlying fee, overlying fee shift to the right, then the interval where, show it again, the interval where both firms are dirty, so where the dirty firm is dirty strategy is dominant, decreases. So it disadvantages the dirty strategy. What you can find? First, we start with the taxation. We find that an increase in the emission tax favors the clean strategy and disadvantages the dirty strategy. There is not a necessary sufficient condition. There is also a monotonically increasing function. So the partial derivative of both underlying fee, the overlying fee with respect to the tax is always monotonically increasing. So as one might expect, tax obviously has a negative effect only on dirty firm, and since dirty firms and has a positive effect to the clean firms, then we have this natural transition. So all the environmental economics literature said that an increasing of tax or a reduction of, for example, the capital emission or the emission permits favor decarbonization of the economy. What is more interesting in this model, and for that reason, this model is more on the theory of insurance demand than from a methodological point of view. There is the importance of being not earnest, but being elastic. Why? Because we find that an increase in the loading factor These are sufficient conditions. Okay, so an increase in the loading factor favors always, for the reason sufficient, the clean strategy if the dirty firm's demand for insurance is inelastic. This is not a big problem because, as I said in the introduction, the motivation of the paper, all the empirical literature finds that the demand for environmental insurance is inelastic. So we are perfectly in line with these empirical results. To see the effect of the shift to the right of the overlying fee, we have a more restricted sufficient conditions. So we need an increase in the loading factor. Disadvantage is always the dirty strategy. If the clean firm's demand for insurance is more elastic than dirty firm's demand for insurance, or if you prefer, dirty demand is less inelastic than clean demand. And this is in line with the paper that to be quickly. The result is a very recent paper, 2021 JIM, in which they find that if an agent is more has an higher risk exposition with respect to another, his demand for insurance is more inelastic. So, sorry, if you go back, it means that in this case, the dirty firm has a more risk exposition. Why? Because since their output is lower, then they have also related to the data property, they have as less financial asset to cover the loss. Okay, so there is called also risk exposition in this case for the dirty firm is good. So we can conclude. We find, I'll tell you this story in these 45 minutes, more or less, story on strategic demand for environmental insurance. Why strategic? Because firms know that their production impact environmental damage. All the literature before SEOG is both deterministic and both not, both endogenous and exogenous. We introduce this poor endogenous loss in which firms take into account that their production increases the environmental damage. So the risk is not exogenous. It's very important. It's very, it changes a lot of the result. Obviously, finite emission taxation can force the market to decarbonization. The dark side, insurance can help dirty firm, or better, insurance has dirty firm more than clean firm. However, an increase in the premium favors the clean strategy if the dirty firm's demand is inelastic, and if the clean firm's demand for insurance is more elastic than the dirty firm, then we have that an increase in the loading factor, and so increasing in the insurance premium disadvantage also the dirty strategy. So one can say that what's mean increasing loading factor? Loading factor captures all the costs that this insurance company have to support. Also, for example, a tax on company. So, for example, if the government increasing the tax on the profits of the insurance company, we have in this case an increase of the loading factor. If remember that the insurance market are competitive, so the marginal revenues is equal to the marginal cost, but not the profits are equal to zero. Okay. So this is one of the ideas. So if, for example, if the cost of the insurance company increases, then the lambda increases, and so we have it can favor if we have this relation between elasticity. So if there is respected the importance of who is more elastic and if the demand for insurance of the dirty film is inelastic. Next step. First of all, abatement choices, because it could be interesting if the tax would be introduced, for example, an end-of-pipe technology, we can have abatement investment, so spillover effect. Could be interesting to expand this model. So, also a more general framework. However, it will be very complicated work with an implicit expected utility. For that reason, decide for a log function. Could be very intense also an optimal taxation, because here the tax is a behavior, is a policy rule, so it's only a unit fee. And also, if the tax is also optimal, also a welfare analysis. Why not other environmental policies? For example, an ETS, emission trade system. Alt-HOV could be different to explain the same risk. So we have to introduce also difference of the risk. And also suggestion from the GERAD audience, so from the floor, truly welcome, because it's also a work in progress, but there's a larger or intervention about it. And thank you very much again to this opportunity.